Hello, my Calc 2 student. Right now, we talk about section 8.7. It's L'Hopital rule. But before we started, I remember you how we found before we found some limits. For example, we have limit x approach to 1. I write something very simple: x squared plus 2x minus 3, x minus 1. If you plug in 1 in your function, you have this rational function is 0 over 0. And because it's rational function, it's polynomial over polynomial, this means you can factoring limit x approach to 1. You have x minus 1, x plus 3 over x minus 1. And then cancel in this part, and now you plug in 1 and you have 1 plus 3, it will be 4. 4. Okay, great. One more example. Limit, for example, you have 2x to the third plus 4x minus 5 over 5x cubed plus 1. But this x approach to infinity. How are we solving this example? We up and down our fraction, we divide by x in the highest degree. Highest degree here is 3. Okay, great. This means if up and down you divide by x cubed, you have limit x approach to infinity 2 plus 4 over x squared minus 5 over x cubed divide by 5 plus 1 over x cubed. Here if we remember what this x is, x approach to infinity, this means 4 over infinity is 0, 5 over infinity is 0, 1 over infinity is 0, and this means your limit is only 2 over 5. Okay, great. But what happened if you have fraction whereas sum of part your fraction is not polynomial? For example, we remember in Calc 1 class we have some special limit sin x over x approach to 0, and we spent time for proving this limit is exactly equal 1. Okay, or something similar like this. But now we have this very useful theorem. It's called L'Hopital rule. And this theorem tells us if you have limit fraction to function x approach to some a, and result, if you plug in a, you have 0 over 0 or infinity over infinity, then this limit is equal x approach to a. Each function you substitute with derivative this function. Okay. How we can use this L'Hopital rule for solving? For example, go back with our special limit sin x over x approach to 0. If you use this L'Hopital rule, we have, first if you plug in, you have 0 over 0, and then you have limit derivative sin x cosine x, derivative x is 1, x approach to 0. You plug in your 0, it will be 1 over 1, this means this 1. You see, counting this limit is much easier than we did before. Okay, doing some examples. For example, number 1, you have limit x over e exponent minus x, whereas x approach to negative infinity. Oh, for checking this limit, first we need to remember what happened with exponential function. Okay, let's go. I have exponential function e exponent minus x. It will be something like this. Y equal e exponent minus x. If x approach the negative infinity, your graph approach the infinity. This means here you have infinity and numerical is infinity, or maybe negative. And this means we inside L'Hopital rule and we can do it. Okay, what is this limit is? A limit. Derivative x is 1. Here is minus e to the negative x. X approach to negative infinity. 1 over infinity, you have 0. Okay, great. Doing one more example. Example number 2. Limit x approach to infinity. X natural log x. Sorry. I think when I copy, I make mistake. Here it will be. I'm doing this one. X approach to 0. X natural log x. This one is correct. 0 plus. Here we remember logarithmic function graph. Maybe just a moment. I'm doing mixed up. First we try rewrite like fraction here. And this I'm doing this trick we use in the future. X I write like 1 over x and multiplied by x, it's divided by 1 over x. X approach to 0 plus. What we have here? Looking for logarithmic function graph, ln x. If x approach to 0, your ln x approach to negative infinity. This means negative infinity here. And 1 over 0 is infinity there. This means we inside our L'Hopital rule. And we can continue. And what we have here, use derivative, we have limit. Natural logarithm x's will be 1 over x. And here will be minus 1 over x squared. And x approach to 0. Simplify. You have minus x squared over x. Cancel it. And this means you have 0. Then a couple of more examples when you can use some special method and then we can use L'Hopital rule. Okay. Question number 3. What happened if you need to evaluate this kind of limit? 1 plus 1 over x power x, x approach to infinity. We don't have any fraction here, no, except inside your base. Okay. But if you plug in x approach to infinity, like base approach to 1, and you have infinity power. And this is big question mark what you have. Okay. Pretend we know what is it. It's some number a. Now I can take it a logarithmic function for both parts. My equation, and then I have ln a. That will be ln limit x approach to infinity 1 plus 1 over x power x. Now, because logarithmic function is continuous function, this means you can switch order. And can I do in this way? Limit x approach to infinity natural log from 1 plus 1 over x power x. Great. What we can do now? Use logarithmic identity. We can rewrite x approach to infinity, x natural log 1 plus 1 over x. And this one we use trick how we did before. This means rewrite like fraction. Natural log 1 plus 1 over x divide by 1 over x. And what we have now? If we plug in x infinity, 1 over infinity is 0, 1 plus 0 is 1, natural log from 1, it will be 0. 1 over infinity is 0. This means here we have 0 over 0 inside theorem L'Hopital rules. Try use what we have here. Limit x approach to infinity 1 1 over 1 plus 1 over x minus 1 over x square divide by minus 1 over x square. Simplify, plugging x equal infinity here, and we have exactly equal 1. Okay, but it's not final answer because we found natural logarithm a equal 1. This means a equal e. And now we remember what is a is limit 1 plus 1 over x power x, x approach to infinity. This is exactly our e. Okay, great, we find finally solving this problem. Okay, one more example. When you have base and power and variable it stays there, limit x approach to 0 sine x to the x power. If x approach to 0, you have 0 in the base, 0 in the power. And question what we have here. Same trick, pretend this is a. This means natural log. Natural log our a will be, well, here I'm switch now. It will be a limit order switch. X approach to 0, natural log sine x power x, and rewrite limit x approach to 0, x natural log sine x, and this is natural log sine x over 1 over x. Great. Continue, but first we're checking. If you plug in 0 here, sine 0 it will be 0. Natural log from something approach to 0 it will be negative infinity. We draw our graph, you can see. And here 1 over 0 it will be infinity. Okay, we can use our L'Hopital rule, and here it will be limit cosine x over sine x divided by minus 1 over x squared, x approach to 0. Write little bit normal writing, and we have here limit x approach to 0 minus x squared over tangent x. If you plug in 0, you have 0 over 0. This means L'Hopital rule is still work. You see, sometimes it's more than one times we use. Okay, for some example, you have minus 2x over secant square x. Now here is great, because if you plug in 0 here, you have 0 over 1. This is 0. But remember, we found natural log a is equal 0. What does mean? Our a is equal 1. In mean, our limit sine x power x, whereas x approach the 0 equal 1. Okay, great. So a couple of examples from your book. Okay, number 24. Number 24. Limit 5x plus 3 over x squared minus 6x plus 2. X approach to infinity. So here for rational function, you can do it two different ways. We can use L'Hopital rule, this means found derivative, use derivative, or you can divide up and down for maximum degree for x squared and see what happened. But here we use L'Hopital rule, it's more practice for us now. Infinity, it will be 5 over 2x, minus 6. If you plug in x equal infinity, here you have 5 over infinity, it's mean 0. Okay, great. But number 22, it's number when you can use only L'Hopital rule, because limit x approach to 1. Here you have a function who is arctangent x minus pi over 4, and denominator is x minus 1. If you plug in 1 here, you have arctangent 1 who is pi over 4. This means pi over 4 minus pi over 4 is 0. 1 minus 1 is 0. Okay, great. Use L'Hopital rules. We have x approach to 1, 1 over 1 plus x squared. This is derivative arctangent, and only 1 in the denominator. Plugging 1, you have 1 half. This is our answer. Okay. One more example. Example number 46. When you have limit x tangent 1 over x, x approach to infinity. Okay, this we're doing our trick when we rewrite like fraction. Okay, limit tangent 1 over x divided by 1 over x, x approach to infinity. 1 over x is 0, tangent 0 is 0. This means you have 0 here, and 1 over x, 1 over infinity is 0. Okay, 0 over 0. L'Hopital rules work. Limit x approach to infinity. We have secant square 1 over x. Here you have minus 1 over x squared. Divide by minus 1 over x squared. Simplify this part, and plugging our infinity there, you have secant square from 0, it will be 1. Okay. One more example. 54. Here we have this kind of limit. A limit where you have x approach to 4 to the right, and here you have 3 times x minus 4 power x minus 4. Okay, continue. What we have now? We pretend this is some number a, and then natural log a, it will be a limit x approach the 4 to the right, natural log 3 times x minus 4, x minus, 4. Use logarithmic density. We write this way. Use our method how we rewrite like fraction. Continue 4 plus, we have natural log 3 times x minus 4, okay, over 1 over x minus 4, and this is, try plugging. If you plug 4, you have natural log from 0, infinity, divide by 1 over 0 is infinity. This means infinity over infinity. L'Hopital rule is working. Okay, great, use. This means all this time we only prepare our function for using L'Hopital rule. Okay, what we have now, it will be 3 times x minus 4, and derivative, it will be 3 over minus 1 x minus 4 square. Okay. 3 and 3 cancelled. You have 1. Use. I use our working with fraction. What we have here, limit x approach the 4 to the plus. We have minus x minus 4 to the square over x minus 4. I think it's this and this cancelled. And if you're plugging 4, you have 0. This means our natural log with a equals 0. This means a equal 1. And our limit 3 times power x minus 3 times x minus 4 to the power x minus 4. This is equal 1 if x approach the 4 to the right. Okay, great. And one more example. I think it's last for this section. What happened 58 if you have limit 1 over x squared minus 4 minus square root x minus 1 x squared minus 4. Okay. And here is x approach to the 2 to the right. Okay. If you plug in, you have infinity minus infinity. Great. But we a little bit work. First we rewrite our fraction together, especially because its denominator same. If you plug in 2 now, you have 0 over 0. This is two-way. Work with derivative. This means use L'Hopital rule or use how we did before. This means multiply and divide for something similar. Okay, then let's do it this way. Little bit forgot about our L'Hopital rule. This means both fraction I multiplied 1 plus square root x minus 1, and I'm divide for same. Because I multiplied and divide for something same, nothing changing, but we can work now. Limit x approach to 2 to the plus. We have 1 minus x minus 1 Here we still have same. Oops, I'm going to root little bit early. Oops. Then I need, okay, I have 1 plus square root x minus 1. Continue. Numerical is 2 minus x, or if we take it minus out, you have minus x minus 2. Factoring our denominator, and simplify, and plugging our x equal to, we have minus 1 over 4 times 2. This means minus 1 over 8. Okay, that's it for today.